Chapters 13 and 14 are on trigonometry. Trigonometry is really what happens when two math disciplines love each other very much and have a baby. In this case, geometry and algebra come together and have a baby called trig. Trigonometry really has the word trigon in it, and trigon means a three-sided shape, just like how decagon means a 10-sided shape, and polygon means any sided shape. A trigon is a three-sided shape, so we're doing triangle geometry. That's what trigonometry really is, triangle geometry. And we start with right triangles. It won't always deal solely with right triangles, but we start by dealing with these right triangles down here. Sides A, B, and C are going to be the three side labels that we typically use. C is always going to be for the right angle. Side C is for the right angle in right triangles. And the side has a lowercase letter, and it's always opposite the angle. So here is side C opposite angle C, here is side A opposite angle A, here is side B opposite angle B. They're always opposite each other like this. The correct term I should be using is subtends. Angle A is opening up onto this point here and this point here. So technically angle A subtends side CB, and that's what we call side A. Trig ratios, sine, cosine, tangent. You've learned SOHCAHTOA, where sine is really opposite over hypotenuse. Cosine is really adjacent over hypotenuse. And tangent is really opposite over adjacent. So if I make up some triangle here, like here's a 3, 4, 5 right triangle, and I call this my angle. This will be angle theta. Theta is a Greek letter. It's literally with a TH pronounced theta. You're going to see it a lot in the next two chapters. Theta means that's the angle that I'm looking for. Well, right now, if I wanted the sine of theta, I would really want to find the opposite over the hypotenuse. Well, the sine of theta is going to be the opposite here is 4, and the hypotenuse is 5. And the cosine of theta is the adjacent, which in this case is the 3, over the hypotenuse 5. And the tangent of theta is the opposite over the adjacent, or 4 over 3. But we can change theta. Theta could be any angle. If I made theta this angle here, in this case I'll just call it x, because why not? Well, now the sine of x, which is still opposite over adjacent, this is now the opposite, because this 3 is on the opposite side of this x. So sine of x is now 3 over 5, and cosine of x is adjacent over hypotenuse, and it's 4 over 5. And tangent of x is opposite over adjacent, and that's 5 over 4. So whichever angle you have, that dictates which ones will be your opposites and which ones will be your adjacents. The right angle is never, ever, ever your theta, because then opposite and hypotenuse are the same thing, and that doesn't really help you with anything. You probably haven't learned the reciprocal trig functions. They're very quite simple. The first is called cosecant. Cosecant is just the reciprocal of sine. It's just 1 over sine. That means since sine was opposite over hypotenuse, cosecant, 1 over sine, is hypotenuse over opposite. Secant is the reciprocal of cosine, so 1 over cosine becomes hypotenuse over adjacent. And then cotangent is the reciprocal of tangent. Now these are just a little bit annoying because you really just wished that the cosecant would pair up with the cosine. But it doesn't. Cosecant goes to cosecant goes to sine, and secant goes to cosine. I'll explain later why that is. It's not worth worrying about now. Cotangent does go to tangent, so that at least is nice. It makes sense. But unfortunately, you wish secant would go to sine, but it doesn't. Secant goes to cosine. So suppose I had some trig ratio, like the sine of theta was 5 over 13. Well, there are now 5 other trig ratios I need to work with. I always have sine, cosine, and tangent. I'm going to give myself more space. And then I also have cosecant, secant, and cotangent. I can find all 6 of these trig ratios knowing only the sine of theta is 5/13. And let me show what I mean by this. I'm just going to draw a right triangle. Now when I pick this tool, it's always drawing a 45-45 right triangle. I don't really like that, so maybe I'll pick another one actually. Sure. This is actually a 30-60-90 right triangle, but it'll work for now. Sine of theta is 5/13. I know this is a right angle, so I can just pick one of these to be theta. I'll just pick this one to be theta, because why not? Well, sine is opposite over hypotenuse. So this right here is my opposite. I know it's 5, and I know that my hypotenuse is 13. So now, if I just label this triangle ABC, whatever, I need to find side A. Well, I can just use Pythag. Remember, the Pythagorean theorem only works in right triangles. A squared plus b squared equals c squared. So I have a squared plus 25 equals 169, which means that a squared equals 144, which means that a equals 12 when I square root both sides. So now I have that my a length is 12, and this is a 5, 12, 13 right triangle. Well, I can find these trig ratios now. I knew that sine was 5/13. That was given to me. But now I know tangent. Tangent is going to be adjacent over hypotenuse, 12/13. I'm sorry, that's cosine. Cosine is adjacent over hypotenuse, 12/13. Tangent is opposite over adjacent, 5/12. And then the reciprocal functions, cosecant. Well, cosecant is 1 over sine, so it's hypotenuse over opposite. But the nice thing, so hypotenuse over opposite would be 13/5. But the nice thing about the reciprocals is they're literally reciprocals. I can just take this fraction and flip it over, and just take this fraction and flip it over. So out of all 6 trig functions, once I find one of them, knowing only that sine of theta was 5/13, I can find the other 5 pretty quickly. Just draw a triangle, use a little Pythag, find what you know, fill in everything else. If cosine of theta is root 2/11. I'm just going to draw a right triangle this time. This is my slightly poor right triangle. Cosine is adjacent over hypotenuse. Well, the adjacent, and it doesn't matter, I'll pick this to be theta. The adjacent side to this is root 2, and the hypotenuse is 11. So I'll do a squared plus b squared equals c squared, do some Pythag. And a squared, it doesn't really matter which is a, which is b, which is c. I mean, c should always be your hypotenuse. A and b don't matter. So a squared is still a squared. B squared is now 2, because the square root of 2 squared is 2. C squared is 121. So a squared is going to equal 119. So a is the square root of 119. Let me stop for a second and make sure that's how I wanted that to come out. Yep, that sounds fine. So now if I'm going to find all my 6 trig ratios again, I have sine theta, cosine theta, tangent theta, cosecant, secant, cotangent. Well, I knew that cosine theta was root 2/11, which means I also know that I'll get that in a second. So sine of theta, well, this is now root 119. So sine of theta is root 119/11. Tangent of theta, opposite over adjacent, is root 119 over root 2. Now here's we have to remember how to simplify radicals. We aren't allowed to have square root or have radicals, square roots, on the bottoms of fractions. So I rationalize by multiplying by the denominator. It's going to turn into root 238 over 2. If that root 238 could simplify, I would simplify it, but it can't. So now for these inverse functions, these reciprocal functions, not inverse, reciprocal functions, this becomes 11 over the square root of 119, and then I'd have to rationalize this. It's really 11 root 119 over 119. So secant theta is going to become 11 over root 2, which when I rationalize by multiplying by 1, becomes 11 root 2 over 2. Finally, cotangent. Well, I had originally, look at the original one. The original one was root 119 over root 2, so it becomes root 2 over root 119. Multiply the top and the bottom by root 119. So you end up with root 138, 238, excuse me, root 238 over 119. You'll kind of get a feel of how these trig functions relate to each other and how you flip them over and how that goes, because there's some patterns you can pick up here that basically, in this case, 238 is always on top, and either 119 is on the bottom or root 2 is on the bottom, depending on which one you're dealing with. Excuse me, sorry. Okay, moving on. If you remember what the word inverse means, if we were in class right now, I'd have you answer this question. But we learned inverses of all types of functions and operations. The inverse of addition is subtraction. The inverse of multiplication is division. The inverse of an exponent is a logarithm. And the inverse of a trig function, we call its inverse trig function. To remind you, inverse, the definition that we really gave was to undo something. An inverse is how you undo something. So when you're doing a sine function, it's giving you a ratio of the sides of a right triangle. I'm going to try to explain really briefly what sine, cosine, tangent are really doing. Knowing right triangles is so important that a long time ago, somebody realized if this is a 3, 4, 5 right triangle, and I take a bigger right triangle, I'm going to draw it the same, but I take a bigger one, 6, 8, 10, these have the same ratio. They're similar triangles. I mean, the division of the sides all gives you 2. So this angle here and this angle here are going to be the same. And so if we could write down like the ratio of these two sides, this is opposite and adjacent. If we could write down the ratio of the opposite side over the adjacent side, in this case that's 4 over 3, we know that whenever we have a ratio that's 4 over 3, we know this angle is whatever that angle is. Let's say it's 20 degrees. I'm pretty sure it's not. Let's say it's like 22 degrees or whatever it is. But if we get any ratio where the opposite side over the adjacent side is 4 over 3, then it must correspond to an angle of 22 degrees. And if we get a ratio where it's 1 to 5, and now I'm dealing with tangent again, well then this angle is going to be some measure, I don't know what, we'll say it's 40. I'm kind of making this up right now. That means the tangent of that angle up there, this angle right here, is 1 over 5. But if we know that the ratio is 1 over 5, we know that the angle itself, we're going to pretend, is 40. So sine, cosine, and tangent are really just collections of all the possible ratios that a right triangle can come up with. I don't know if that really makes sense or not. I think as the chapter goes on, that'll get more and more clear. But the point is, whenever you have plain old sine, you're getting the ratio of side lengths. You use plain old sine to find lengths. And if you have sine inverse is how you undo sine. That gives you an angle. So working with sine spits out lengths. Working with sine inverse spits out angles. So the result of this is a length. A distance, the result of this is an angle measure. And here's what that means. Right now I want to find angle theta, knowing that the hypotenuse is 6 and the opposite is 4. Well, since I have opposite and hypotenuse, that is sine, because sine deals with opposite and hypotenuse. Right now the sine of theta is 4 over 6. I want to know what the actual angle is. I want to actually find angle theta. So if I take a sine inverse of both sides, because whatever I do to one side, I do to the other. If I take a sine inverse of both sides, and 4 6 I can reduce to 2/3. Well, since inverses undo or cancel whatever's been done, these cancel each other out, and we just have theta equals the sine inverse of 2/3. And then it used to be back in the old days you'd pull this up on a chart or play with it in a slide rule or something, I'm not even really sure. But here I just press on my calculator second sine. Second sine pulls up sine inverse, so we have the sine inverse of 2/3, and that tells me the angle measure. The angle measure, I have to put this in degrees. You'll have to do that later. You have to do it now also. If you press the mode button. Your calculator right now might be in radians. You want it in degrees for now. We'll talk about radians later. So I do sine inverse of 2/3, and I get 41.8 degrees. The degree measure, the angle measure, was 41.8 degrees. So you use sine, cosine, or tangent inverse to find angle measures, and plain old sine, cosine, tangent to find side lengths. Over here, the sine of theta is 5/9, so theta is going to be the sine inverse of 5/9. Which is 33.7 degrees. If the angle measure never actually looks like the triangle, don't worry about it. I'm just kind of sketching pictures and going for it. They might look right, they might look not. That's not the issue. As long as the math works out, that's what matters. Okay, so now with sine, cosine, tangent, inverse, sine, inverse, cosine, inverse, tangent, we can solve any right triangle if all we have is 2 bits of information. So right now, solving the triangle means find all the missing sides and angles. So I want to find side A, angle A, and angle B. Well, side A is going to be pretty easy. I just Pythag. A squared plus B squared is C squared. So that's A squared plus 64 equals 121, which means that A squared equals 64 minus 121, which is 57. So A is root 57. Don't make that a decimal, just leave that root 57. Now I can find my angles. I'll find angle A. This is going to be cosine because I have adjacent and hypotenuse. So if I do the cosine of theta, I know that comes out to 8/11. Since I knew the ratios and I'm trying to find the angles, I'll do a cosine inverse of both sides. And that gives me that theta equals the inverse cosine of 8/11, which is 43.3 degrees. If I really wanted to, I could also do a sine inverse and find B. But at this point, since I know I've got a right triangle, and I know angles A and B have to be complementary, they have to add up to 90 degrees, this must be 46.7 degrees, because those add up to 90. I've now solved the triangles, found all the missing sides and lengths. So here I only have one side and one angle, so I know automatically that this right here has to be 40 degrees. That's pretty simple, because those have to add up to 180. So I'll try and find side length B. Well, here I have opposite and adjacent, and that's tangent. So the tangent of 50 degrees is my opposite over my adjacent, and I'm going to solve this equation for B. So I multiply both sides by 4. If I do this side by 4 and this side by 4, I get 4 times the tangent of 50 equals B, and I just calculate that. I'm going to break everything. 4 times the tangent of 50. So side B is 4.77. Now I can either do Pythag and find my hypotenuse length C, or just do some more trig. I'll do some more trig in this case. I always want to deal with the number that I was given, not the number that I found. Deal with the number you're given because you know it's correct and there's no rounding errors. So if I want to do adjacent over hypotenuse, that's cosine. So the cosine of 50 is adjacent over hypotenuse, which is 4 over c. Now, I don't really like having c on the bottom of this fraction. I can live with that if I wanted to, but I could also do secant. The secant of 50 is hypotenuse over adjacent, 50 c over 4. And the way that you calculate secant in your calculator is you just do 1 divided by cosine. 1 divided by cosine is secant. So the secant of 50 is 1.55. Multiply that by 4. You get 6 point something. 6.222. So c is about 6.222. Remember, the hypotenuse has to be the longest side, so I'll check to make sure that my side C is longer than sides A and B, which it is. If I wanted to check with Pythag and see if 4 squared plus 4.7 squared equals 6.2 squared, I could, but I'm pretty sure that's good, and I'm going to keep moving. There are special right triangles that you need to get memorized. We're going to use them so much, and they'll be on your SAT and your ACT. One of them is a 45, 45, 90. If you have a 45, 45, 90, if this is side 1, if that has a side length of 1, and this is a length of 1, well, I do Pythag, and I'm doing 1 squared plus 1 squared equals c squared. So really 2 equals c squared. So c is root 2. This right here is root 2. It goes 1, 1, root 2. But what's really more useful, instead of calling this 1 and 1, is to think about it like it could be anything. If this right here was any possible length, this here would be the same length. Because it's a 45, 45, it means that's isosceles. Those two x legs are the same. Well, now I do x squared plus x squared equals c squared, which is really 2x squared equals c squared. Square root both sides, and you get root 2 times x equals c. So this length here is really root 2x, we'll say. Root 2 times x. The other way this can be done, and this is kind of how you're going to see this more, I think I'll leave it like that for now. Over here, on the 30, 60, 90, the shortest side length. So here's a nice little trick. Oh, I have those numbers switched, excuse me. This should be the 60 here, and this should be the 30 here. Here's a nice trick about all triangles. The smallest angle always opens up, subtends the smallest side. The biggest angle always subtends the biggest side. And so that means that the middle angle will subtend the medium length side. So you can always kind of match up an angle to a side that way, knowing that little trick. So let's say the smallest length here is a 1. Well, this 30, 60, 90 is kind of half of an isosceles. If I draw the other half of the triangle over here, this would be 30, and this would also be 60. And if I think about this triangle, if this is isosceles and this right here is length 1, excuse me 1 second. Let's actually not worry about this other triangle here for 1 second. If we just think about the trig that's taking place here, if I wanted to find the hypotenuse, find length c, well, I can do, if I just called this length 1, I called that a unit length of length 1. This is sine, opposite of hypotenuse, so the sine of 30 is 1 over c, which would really mean that 1 over sine, or cosecant, the cosecant of 30 is c over 1. So I'll calculate the cosecant of 30. That's 2. In a 30, 60, 90 right triangle, the hypotenuse is twice as big as the short leg, the leg that's opposite the 30. So if this is 1, this is 2, and I do some Pythag, 1 squared plus b squared equals 2 squared. So 1 plus b squared equals 4. So b squared equals 3, and b is root 3. So this length right here would be root 3. And if I change these to x's, if instead of calling this length 1, I call this length x, this would be 2x, and this would be root 3 times x. And we're going to come back and talk about those a ton in trig. They come up all over the place everywhere, and they're very useful. So we'll skip this for now, and I think we'll just call that a day. So to recap everything, trig functions allow us to find the ratios of two sides of any right triangles if you have given an angle measure. So when you have an angle, you're allowed to find a ratio. Inverse trig functions, like sine inverse, cosine inverse, they let us find an angle measure if we're given two sides. Reciprocal functions are just trig functions flipped over. 30, 60, 90, and 45, 45, 90 special right triangles are really important, so work on memorizing everything about them. This video, like most of the videos in this chapter, are going to be kind of long, but we're going to move slowly, so that's a good thing.